catchment runoff for next few days. And when you route that water in the river, you have additional lead time, and that gives you that how much flow in a river you will get in next few days. So that is short term to medium term forecast. And then you use various statistical tool, other methodology to calculate seasonal or long term forecast. Now, when you have this precipitation forecast for next few days or meteorological forecast for next few days, you can use this in various modules of MIKE software for different type of study. So we have MIKE Hydro for channel flow and control structure. We have MIKE Plus for urban or coastal flooding. We have MIKE 21 for 2D overland flow. MIKE 21C is for river hydraulics and morphology. MIKE C, like I said, is integrated catchment modeling, so surface groundwater interaction, and FEFLOW is groundwater modeling. All this software, if you have the info, uses precipitation means as one of the input. And when you have precipitation data for next few days, you have runoff for next few days. And all this process can be automated through database management system, that is MIKE operation. So this software gets registered into MIKE operation, and all the process that is involved from data fetching to data dissemination is automated in this database management system. So if I talk about any early warning system, so basically you can divide that into 4 components. You have data acquisition system. You need to have real-time data from field to your FEWS system. So it can be ground station, or it could be satellite based information. So telemetry, IMD has put thousands of stations over India. So, and that they are providing those data in real time. So you can use those data. They are also providing, IMDs also provide this data in raster format. You can also use that data. Then near real-time precipitation is provided by GPM. So 5 to 6 hours of lag period is there. But almost in real time, you get this satellite-based precipitation. And then there are forecasting agencies, IMD, NCMRWF, GFS. They provide 3 to 10 days of forecast. ECMWF is also one of the agencies. They provide 15 days of forecast, quantitative precipitation forecast. So all the data which you get from various sources becomes part of your data acquisition system. Then you have workstation and servers, because all the process is going to be in automation mode. So all your system should be open 24/7. So for that you need a server for real-time projects and good quality workstations. So the flow structure from how this data import will take place from one server to another server, how this flow structure will be maintained, because it also requires dissemination. Then firewall, its safety and security needs to be maintained, and there should be some backup system, so that if something happens in the data center, it can be restored easily. So with this concept, you need a management system. And then you have obviously modeling tools, which you will use the data from the data acquisition system and will process it to generate various results. Normally we use for a water sources system, we use rainfall runoff model. If there is snow in the catchment area, then you also need snow melt model, and then you need hydrodynamic model. If you also to route the water from in the open channel, and if there is flooding in some of the in any of the stretches, then if you want to generate flood map, you need flood model as well. Now this, so and there could be many other models if you are interested in surface groundwater interaction, or how much water will be available for extraction from groundwater. So there could be different analysis, or it could be something water quality issues, so forecasting of some water quality parameters. So then you will need additional modules. So depending on your project requirement, you need different modeling tools, and these modeling tools you need to activate in the term of forecasting system. So forecasting system is nothing but you have in the rainfall runoff model, you have time step, that is you have rainfall for next 10 days from now, so you will get runoff from next 10 days. But to make it automation, we need to devise a plan where every day your model is shifted to till time of forecast with real-time data, and afterward with meteorological forecast data. So that's basically more a sort of setting your the hydrological model, and then you can use this information and some statistical analysis to generate seasonal or extended hydrological prediction, or you can use this information for reservoir operation and planning. So depending on your project requirement, so you can use different modeling tools, and once your model is simulated, the results needs to be disseminated on website, through mail, SMS, through daily reports to different workstations. So that's basically dissemination of output. So these are the four major components of any early warning system. Data source, like I said, it could be point data, it could be raster data. Now, if I talk about modeling system, rainfall runoff model, so what it does is, till time of forecast, when you have real-time data, it sets the initial condition of the catchment. Initial condition of the catchment means the moisture condition of the catchment. So you have, whenever there is a precipitation, obviously it will be, some of it will infiltrate, other will move as surface water as overland flow, and some of the water will be lost as evapotranspiration loss. So how much moisture, again, the infiltrated water, it may get transpirated, or it can percolate into the groundwater. This groundwater can again move as a base flow to the river system, or it can go into deep percolation. So at every stage, its model calculates that how much moisture is left in various zones. That's basically, I'm talking about the NAM model. That's a conceptual lumped model. I'm not going into too much detail, but this way, with real time, at every time step, the moisture condition in different zones keeps on changing, and that is set by a real-time data set, real-time information, and on that you put forecasted precipitation and you get the updated runoff. And every day this time of forecast will change. It will go to next day, then you will have till here you will have real-time data set, and for next days you will have 10 days forecast. So all this process is automated through scripting. So basically you have real-time data set, you have meteorological forecast, and then you can use historical record or climate model to extend this prediction. So there is a difference between forecast and prediction. Forecast normally we say when we have some we are using some quantitative precipitation to generate the runoff. So it's more a sort of dependable kind of thing. Prediction is more like if you are using some historical information and generating some information from there. So basically simple, you have different sources of precipitation. You use that precipitation source. Again, I'm talking about MIKE software package. This process will be little different in a different type of model. So the first thing that we do is using different sources of precipitation, we calculate catchment rainfall. Then we use this catchment rainfall to generate catchment runoff, and then this catchment runoff enters into hydrodynamic model, and then you get the flow, this inflow and water level at different cross sections, and then you have this information for the forecasted period. Then you have inflow and water level forecast at the different cross section. Then when you see this inflow and water level at different sections or along a river in L section or in cross section, you know at what cross section water level is going above levee point, means above cross section boundary. So those are the locations where you have flood scenario, and at what time step that water level will breach the levee point. So then you will have flooding, lateral flooding in those area, and then you connect your flood model and generate flood inundation maps. So this is the basic or in general process. And again, if I talk about flood, then it's not only the riverine flood, it could be a combined effect of fluvial flooding, pluvial flooding, and coastal flooding. So in a urban area especially, you can have at the same time your river is carrying lots of water, flood water in your urban area. At the same time you have intense rainfall in that area, and also if that urban area in the coastal region, you can have that flooding can be further affected by storm surge or extreme tides. So model should be capable of generating flooding from all the three scenarios, and MIKE Plus software or MIKE Plus flood has capability to generate this type of flooding. Now when you have generated this data acquisition system, models, all these things needs to be incorporated into data management system, and MIKE operation allows it's a single IT system platform where you have time series, GIS, model, various other tools, scripting, automation. All this capability is incorporated into this MIKE operation system. So time series, you have all the data acquisition system data. GIS, it has GIS, you can process DM, cross sections, snow cover. You have all the modeling tools incorporated inside MIKE operation, and then you have scripting and automation tools for real-time management. Now, if I talk about project, then obviously one of the project where we implemented this is Bhakra Vyas Management Board, and there it has they have to manage two reservoir, main two reservoir, Bhakra and Pong. Bhakra reservoir is on Satluj River and Pong reservoir is on Vyas River. Now, in Satluj, two-thirds of the catchment is in Tibet region, and there is no exchange of real-time data information between Tibet and India. So there is no information, or there is no hydrological information for almost two-thirds of the Satluj catchment area. Second problem is 60 almost 65% of that catchment is snow fed, and then you also need a snow melt model or a snow forecasting model to analyze how much flow will come, especially during lean period. Then they did not had before this flood warning system or reservoir operation system. They were simply using some traditional method which is based on dry dependable mean flow. So they had a long time series, and they have extracted dry year flow, dependable year flow, and mean year flow. And they were considering that, okay, if dry or dependable year flow आएगा depending on IMD suggestion. So they were using simple that time series for reservoir operation. So there was no use of any real-time information for the reservoir management. And obviously they are having problem of flash flood and cloud burst, especially near reservoir area. So these were the main issues which we wanted to tackle using this RTDSS system that we developed for BBMB. So these are the characteristics. You can see that this whole area, it's in Tibet region, and this is all area that is basically snow fed, and there are you can see that how 67,000 square kilometer total area, and Byas 12,000 and Satluj 55,000, and two-thirds of 55,000 is in Tibet region. So what we did is we created a RTDSS system there, and so what we did is for the Tibet region we have used satellite based precipitation, that is GPM data, and we calibrated this complete catchment at this Khab location, which is basically the starting point of in the Indian region. When water from Satluj enters into India, that area is Khab, where we calibrate our model. And then for downstream area we had also lots of station, point station, means ground stations, and then we have used lots of satellite based information and created this rainfall runoff model, then hydrodynamic model, and then what we are doing is we are forecasting these flows at certain points on the river system, and then tracking the flow here. So if there is certain precipitation in this area, obviously the flow will increase at this point, and then you will have a lead time of this much period till this water reaches the reservoir. In normal flow condition, it almost 3 to 4 days it takes for this water to reach the reservoir. So enough lead time. And then also we have this flows from the downstream area, and it gives us a good lead time that how much flow is going to come to reservoir, this and this reservoir. This here this is all in India region. And here we have Pandor Dam, which releases certain amount of water from this basin to this basin and generates power. So inter-basin transfer is also there. What we are doing is we are using these models to provide a forecast, and forecast is available at all the discharge sites as well as at the reservoir. So you have the when you have DBMS system, it's Postgres SQL based DBMS system, and you can post process data in any format as you like to. So you can see the result in time series format, you can see the result in daily average flow format, or any other format which you want. So here is just a summary that's showing that next 10 days how much flows will come, and accordingly what will be the level of reservoir in next 10 days depending on some outflow decision. So this way we are generating results, and based on these results decision is taken how much water they can release. This is the meteorological forecast for next 10 days. Then especially during summer period, during when summer starts, March, April, snow melt starts, and reservoir level is low, the irrigation demand is very high. So it's very important to know that how much snow melt will come in next 3 months. So basically April, May and June, because from July again monsoon will start. So in April, May and June, when water demand is very high, how much flow can be released from reservoir will depend how much flow from snow melt will come to reservoir. And for this 3 months forecasting is required. It's not that complicated, because because in a snow when you are having winter rain, it's getting accumulated in the catchment, so that you call as snow accumulation. So when you have the snow accumulation, how much snow is accumulated in the catchment at the end of or at the start of melting period, then you know that based on temperature only it will affect how much of that snow is going to get melted. And how much of the snow will get melted in March, April, May or June will depend on how temperature is going to be there during this period. So a temperature forecast for next 3 months is required. A good quality temperature forecast for next 3 months will give you a good quality snow melt forecast. Unfortunately, there is no agency which provides 3 months forecast. So we need to do some ensemble study. We need to do some basically we calculate average temperature, and then you apply, like if temperature will increase by 2 degree or will decrease by 2 degree, different scenario you need to generate, and accordingly you estimate how much runoff it's going to generate for in next 3 months, and based on that you take decision for the reservoir operation or release of water. So this is all this project in BBMB. In Krishna Bhima project, you have here actually there are 46 number of reservoirs, and there is huge rainfall in the upstream area and almost no rainfall in the downstream area. The upstream area, due to high rainfall, always gets flooded, and there is a scarcity of water in the downstream area. So, a effective flood management and reservoir operation system is required in the Krishna Bhima project. So there also we have developed the same system, data acquisition, then MIKE hydro river model, means RR and SD model, and then MIKE hydro basin, means reservoir operation modules. So, and then optimization of reservoir operation based on forecasted inflows for next 10 days or next 3 days here in this case. So this way we are doing the operation in Krishna Bhima. In West Bengal and Chennai both has urban project. In West Bengal it's a water supply project, and in Chennai it's drainage project. But for both project we have developed forecasting system. So, but in West Bengal, what we did is it's a water supply. Here is it's surface water supply project. So, and the intake, water intake for supply is very near to sea, and at sea there is influx of this salinity at this site. So if you will see, as you go away from the sea, ocean, this salinity decreases, and at the river intake point, some period you have salinity above critical, and sometime you have salinity below critical level. So almost in a year, you can see that for 5 to 8 months, salinity is below critical level, and it can easily take water for the supply purpose. For 2 to 3 months, salinity changes with respect to high tide and low tide. So when there is low tide, salinity is below the critical level, and if salinity and when it's high tide, the salinity is above critical level. There is daily variation also. So it's very important to critically have a track of whether salinity is above critical level or below critical level. And then for 1 to 2 months, there is a situation when salinity is always above critical level. So you need to find alternative source there. But almost for the 10 months, if you can manage effectively, you can get water without salinity or without the salinity above critical level, which is safe for the supply. And then for rest period, you can find alternative source. So still we are working on the alternative source, but this is a live project, and here this means early warning system is important, not only for water level or flooding, but also for salinity forecast. Then also, obviously, if there is a flooding in this area, or then obviously water supply will also get impacted in that case, and that's why even flood forecasting model has been developed for this area. If I talk about Chennai, then here we are doing this 3-way coupled flood modeling, this coastal flooding, riverine flooding, as well as pluvial flooding. So this is another example. There is another project related to morphology, and here what we did for is it's a little different project, but here we were supposed to predict the change, the vulnerability of a area which is along the this river, and this Rapti river actually it changes its path. It's every few years, and making a prediction there is very critical, and we have applied certain methodology to predict the change in the river morphology. We have identified few vulnerable sites, and then we have automated this process where a change in bank level can be predicted, and accordingly it can be managed. Though this was one of the one of the what you say test project where we tried. It's not that much accurate, the prediction, but it at least it gives us idea about what are the sites where we need to critically analyze and accordingly take decisions. Second level study, it was only a first level study, and second level study will come out soon for this area. Then in all this project, one of the component is data acquisition system, and getting this data, collecting this field data, especially for countries like India or developing countries, it's very costly affair. Putting sensors at the sites, getting real-time data from that site to your data center, managing and then managing those data, it's very costly affair. What DHI has tried is use some global hydrological model using satellite based information only, so that the ground data requirement of ground data can be avoided. And the reason is because now we have a lots of global data sets available, and we just need to find a way to extract particular parameters, catchment parameters from those global data set. So what we did is it's the same NAM model. So from the global data sets, we identified different types of data set, and we tried to estimate parameters of these of a NAM model from the global data sets. Obviously, precipitation data also we used only satellite based precipitation, because we have real-time near real-time precipitation source, that is GPM, and we have forecasted precipitation source, again satellite based. So we can create a rainfall runoff model. We can use precipitation for rainfall runoff model from satellite based data set. Then there are other parameters like all these NAM parameters. If you will go in details, basically it calculates the moisture conditions in different zones, in the surface zone, in the subsurface zone, in the groundwater zone, and then accordingly it calculates this the runoff, overland flow runoff, interflow or base flow. Now only the whole idea is to estimate the moisture condition in those zones, and we use this global data set to estimate the moisture conditions, and then we apply some routing method to calculate the travel time. And this almost for whole world, uh, from plus 66 degree to minus 66 degree, um, except for some this Arctic region. uh, we have this global hydrological model ready, and it has been released for public. And the quality, if I say that rainfall runoff model quality is around point r square is zero point 0.6, water balance plus minus 5%. uh, the average, some of the area, some of the region, we are getting a very good result, but there are certain problem in some other area, and average is zero point 0.6 r square. We are still working on that, and we are expecting that the result will improve in our next release. You can this for this, what you need is a user ID password. You can select your catchment area. It means anywhere in India. Just log into this DHI account, and then you can see for any catchment area, any river point. Just you need to select your catchment area and the point where you want to see the result, and you can generate 10 days uh, the runoff forecast or the flow forecast for that river point. So, and that you can use for various types of analysis. This is something we are trying, and we are trying to improve on that. So still we are working on that. That's why I have not put a live demonstration of this system, but this is something we are trying to get it improved, and make it an important product in near future. So yeah, that's it from my side. Thank you. Now you are open. If you have any query, any question, you can ask.
Sir, there are a few questions.
Mhm.
The first one is, does IMD NCMWRF provide daily data with 5-7 days lead in .grib or net CDF format like ECMWF?
Yes. All these data source that means whether it's IMD or GFS or NCMRWF, all they provide either in NC format or GRIP format.
I think they are not available in raster format only for different short, medium range lead times.
No, they are providing data in NC, and
Sir,
NC means net CDF format or GRIP format.
sir, can you please mention the website for the same?
Website for the same.
Because I'm able to see the raster data sets, but I'm unable to see the .grip format data sets, means point data sets for graded
Just
data.
for NCMRWF, na?
Yes, sir.
Just give. I hope I will just check in the database. I don't remember. Just give me a minute.
Sure, sir.
Mm. It's FTP dot. You just need to go to, it's a FTP site, ftp.ncmrwf.gov.in, and there you have in public outgoing IND, means you can explore your area under that folder, which area you are working in, and you can get, there is in outgoing, there is IND region for the Indian region, in 0.25 grid size. Basically we are using that file to for this rainfall data. It's in GRIF 2 format.
Okay, sir. Thank you, sir.
There is a, means you just you just check, because they use a password also there. We are using here anonymous password to use the data. Otherwise you can if that password, I think it's they have provided for us, but if you are able to log in, it's fine. If you are not logging, if you ask for password, you can contact NCMRWF from their site and ask for a password.
Okay, sir.
Sir, there is another question. Please discuss about the Chennai project also.
Yeah, in Chennai, what actually it's for the Kovalam region. Let me open this. Okay, my screen is, just a minute. Let me share my screen again. Yeah, so in the basically it's Kovalam area, Kovalam basin of the of this Greater Chennai Corporation. So in the Kovalam basin, it's near this sea, and you have this river system flowing through this area, this Kovalam area. You can see this river, and what we did is we have created a mesh file for this area, and that mesh file includes the buildings detail, the road line, railway link, and then we all the rivers, and then using this we use this mesh file as a and then on that mesh file we have incorporated a 1D model. So whenever there is a flooding, there is a excess water which can breach that river, so it goes into the mesh region and generates flood. We have used this sea level as a boundary condition, and then whenever there is high tides or something, basically we have the tide forecasting also using CMAP. So we use those information, and then if there is some tides which can enter into this this basin, that component is also incorporated. Then since it's a mesh file, any rainfall is happening in this area also accumulates in the catchment. So pluvial flooding means we have also generated the drainage network map of this area. So I have a drainage network map with manholes all along this area. So whenever there is rainfall in any of the grid area having manhole, then the water for each manhole we have a catchment. So like thousands of manholes and For each manholes, we have a separate catchment area. Whenever there is rainfall in that area, water flows to that manhole and from manhole to manhole. And if that inflow is more than if that flow in the manhole means if rainfall or runoff is more than the capacity of the manhole, it will cause inundation in that area. These manholes again is connected to river at different locations, and if river level is high, then obviously the water will not go into the river, and or maybe there is backwater effect, and it can cause further delay or stagnation of water around manholes. And then obviously if there is more water in that river system, then it can go into the basin and can cause flooding. So it's basically a sort of three-way coupling where you get inundation. You can get inundation due to heavy rainfall, due to the river overflow, due to coastal high tides, or the combined effect of all these three. So this way what we are doing is, again we are using the same this model. You have rainfall forecast for the future period, you have flood scenario for the future period, and accordingly you take a decision. Okay, this area is going to get inundated. We need management in that area. If it's extreme flood scenario there, then you can ask NDRF team or some accordingly you can you can manage that. At least you can save lives in those area where there is a extreme flood forecasting is there. So this is a type of project that we did in Kovalam Basin. Any question?
Yes, sir. There is further one more question. That is, since FE flow is all in one model, does it contain the features of other models?
No, FE flow is basically a groundwater model, and especially for groundwater analysis only we use FE flow. It does not have component of like surface groundwater interaction, or we do have a different tools where we can incorporate the output of one model into FE flow. But I think we have developed one tool for coupling the MIKE C output into FE flow, but no, it means it does not get connected like other software. So that's for a specific analysis only, and there is no need. Only for water quality means FE flow you can connect with Ecolab for the quality parameters and the output of a particular MIKE C model. Otherwise, there is no other tool to connect to FE flow, as per my knowledge. I hope this is what you have asked.
I think so. Last question, sir. That the website which you have asked, no, NCMRWF, that the Ayushi Panchana search, and she is saying that it is not working. Can you please share some more light on it?
I will have to. What I will do is I will check, because I will have to check that if data is available on that server, because it's working in BBMB. Right now I'm not in BBMB project, so I will just have to check if in last few months if it has been changed, then I will give you the revised link. I will have to check.
Okay, sir. I think you can mail me, then I'll share it with the.
Yes. Yes.
So there is no more question in the chat box. So I thank you for sparing your valuable time and delivering a real-time forecasting lecture that how it is managed for Indian river basins. So thank you very much.
Thank you.
Dr. T, you have any say?
No, I think thank you so much for your presentation. It was wonderful. And I could see that you have a broad range of products that can be used for different types of applications. My only question was that um, in the Indian context, you have sparse data, you have data issues. So when you develop a model for a particular project or a particular water agency or a state or a municipality, um, how do you convince them or convince your modelers that you have achieved a decent level of calibration and validation, because sometimes you may not have the real data that is required in some situations?
Yes. So what we do is number one, wherever there is data scarcity, we try to get information from satellite-based data source. So there are multiple satellite-based data source. We don't use all those data source as it is. First, we process those data source and then apply bias analysis, because different data source has different types of biasness in that. And once you apply the bias correction, because the whole idea is with this data source you need to achieve a good calibration range. So we expect that there will be biasness in the satellite based data source, so we don't use it as it is. Apply required bias analysis and then check if our calibration is within the expected range or not. And then once we achieve means our target basically is r square should be more than 0.75, and water balance WBL is plus minus 5%. So we try to achieve this water balance from point data source, from grid data source, from source A, B, C, whatever we get. If we are not getting any of this, means in many of the cases it happens that this data source is not adequate, then we suggest client that if you can install certain rain gauge station at, we provide the locations also, that if you can install certain stations at these locations, you can get your model calibration will get improved. In BBMB especially, why I'm saying you this is, it depends, suggestion depends on which type of organization you are working. So in BBMB they have installed, first we suggested for almost 100 stations for different type of data, and they have installed those stations, and we use that in the model for the model calibration. So
Okay. Yeah, thank you so much for your clarification.
yeah.
So thank you, Manish Kumar, for sparing your valuable time. And please share the presentation so that I can share it with the participants.
Sure,
Okay.
sure.
Okay, thank you very much.
Okay, then I will leave
Yeah,
now.
yes. Yeah, yeah,
Okay,
please, please.
thank you everyone.
Thank you.
So, Dr. T, we missed one presentation in between, that is extreme precipitation and flood, and we have 45 minutes around. So I think that I'll take one case study on extreme precipitation and flood, and we'll try to complete it within 45 minutes or so. Will it be fine?
Yeah, that is because you have something tomorrow, I think, right?
No. Today we have that presentation from 5 to 6:15 p.m. wherein we have
because you got the you got the panel.
The panel
So
discussion.
you got the okay, no problem. Go ahead.
Okay. So I'll need 5 minutes. In 5 minutes I'll start my presentation.
Sure, we can take a break for 5 minutes. Yeah.